Hello and welcome. In our lesson today, we are going to discuss equilibrium and the factors that affect the equilibrium. Now for this discussion, I'm going to use our previous example of ammonium chloride. Now if we were to have ammonium chloride in a closed container, now a closed container simply refers to a container or a vessel that is tightly secured, therefore preventing the reactants or products from escaping into the surrounding. Now, if we had such a case, and if we were to heat the ammonium chloride, thermal dissociation will take place. This simply means ammonium chloride is going to dissociate to form ammonia gas and hydrogen chloride gas. Now, initially, at the beginning, we had a high concentration of the reactant, which is ammonium chloride, because the reaction is yet to start. Now, when you start heating, the forward reaction takes place. Now this continues until you have quite a few of the products being formed. Now once some of the products have formed, you will find that some of these ammonia and hydrogen chloride will start recombining with one another to form ammonium chloride. So at this point, we are having the forward reaction taking place, whereby ammonium chloride is dissociating to form ammonia gas and hydrogen chloride gas. Yet at the same time, we are also having the backward reaction. These two products are recombining with one another to form ammonium chloride. So this continues until it reaches a point whereby the rate of the forward reaction is equal to the rate of the backward reaction. That simply means they occur at the same rate. Now when this happens, the reaction has attained a state of balance and it's said to be at dynamic equilibrium. So what do you mean by dynamic equilibrium? Simply means that the rate of the forward reaction is equal to the rate of the backward reaction. They occur at the same rate. And because of that, we are going to have equal concentration of the products and reactants. Now there are certain factors that affect the equilibrium. This simply means that they have the potential to shift the equilibrium, either favoring the forward reaction or the backward reaction. Now these are concentration of the reactants, pressure, temperature, and lastly, catalyst. So we are going to discuss these factors. Actually, we are going to discuss three of these factors based on the Chatelier's principle. Now, according to Chatelier, he stated that if you were to change the conditions within a system that is at equilibrium, what happens is that the system will react in a way that opposes the change. Okay, basic explanation is this: you change any of the condition in a system, the system will act in an opposite way. A good example is this: if you increase the pressure of a system, what will the system seek to do? When I talk about the system, I simply mean the reactants and the products. So if you were to increase the pressure, the system will act in an opposite way by decreasing the pressure. You increase the temperature, the system will seek to reduce it, and so on. So you change the condition of a system in equilibrium, then the system itself will work to oppose the change in an opposite way. Now let's discuss pressure. Now pressure only ever affects reactions involving gases, not liquids and definitely not solids. And the reason for this is because unlike solids and liquids, pressure gases can actually be compressed and therefore altering the pressure. Now, let's imagine we have this reaction. We have two reactants, A and B, reacting together to form a product, which in this case is C. So we have 1 mole of A reacting with 2 moles of B to form 2 moles of the product, which is C. Now let's look at the total number of moles of the gases on this side of the reaction, on the reactant side. We have 1 plus 2 giving us a total of 3 moles. What about on the product side? We only have 2 moles. Now when you increase the pressure, the system will act to decrease the pressure. And how does it do so? By favoring the reaction that produces fewer molecules. And this is just imagine you are adding pressure and the system also seeks to increase the pressure. What you're essentially going to have, you're going to have a build-up of pressure and pressure and pressure, which will make it very dangerous for that system. So instead of that happening, if external pressure is increased, the system seeks to reduce the pressure within. Now, it's going to favor the forward reaction. Why? Because the forward reaction is the one that produces fewer particles. And that is that. Fewer particles means fewer collisions, means less pressure. So we are going to get more of C being produced and less of A and B. Why? Because A and B are being used to form C. What about if we decrease the pressure? If you decrease the pressure, the system will seek to increase it by favoring the reaction that produces more particles. And therefore, it's going to favor the backward reaction, which leads to the formation of A and B. So how does that affect the yield of C? It lowers the yield of C, production of C, because C will be used in this case to form A and B. Now, let's do an actual example of a chemical reaction. Now, for this discussion, I'll be basing it on the Haber process and the contact process. Now, the Haber process is the process that is responsible for the manufacture of ammonia gas. So, nitrogen gas combines with hydrogen gas to form ammonia. Now, let's look at the number of moles on the reactant side. So, we have 1 mole of nitrogen gas reacting with 3 moles of hydrogen gas. So, a total of 4 moles on this side. What about on the product side? We have only 2 moles of ammonia gas being formed. So, 4, 2. Now, a reminder, an increase in pressure favors the reaction that has fewer moles or fewer molecules. So, if we want to increase the the pressure, what will happen is that the equilibrium will shift to the right, and therefore the forward reaction will be favored. That means a higher yield of ammonia will be produced. Now, this knowledge is actually very useful in the industrial process. So high pressures means a higher yield of ammonia. So that means that for the optimum pressure maintained within the Haber process, it needs to be quite high. But maintaining high pressures is very expensive. So a compromise comes in at about 200 atmosphere. So this is the optimum pressure that is maintained in the Haber process. High enough to favor the forward reaction, but not too high to be astronomically expensive. Now, let's talk about the contact process. Now, the contact process is the one that is responsible for the manufacture of sulfuric 6 acid. In this reaction, sulfur 4 oxide reacts with oxygen gas to form sulfur 6 oxide. Now, again, let's look at the number of moles on the reactant side. We have 2 moles of sulfur 4 oxide, we have 1 mole of oxygen gas, a total of 3 moles on this side. What about on the product side? We only have 2 moles. Therefore, if we were to increase the pressure, it's going to favor the forward reaction, ensuring that a higher yield of sulfur 4 oxide is produced. What if we lower the pressure? If we were to lower the pressure, what happens is that the system will act in a way that will increase the pressure. You're lowering the pressure, don't itaongeza. That is simply what it's telling you. So if you lower the pressure, the system will act in a way that increases the pressure. So how is this attained? By favoring the reaction that produces more molecules. And this, of course, is the backward reaction. So you're going to have sulfur 6 oxide breaking down to form sulfur 4 oxide and oxygen. How will this affect the yield of sulfur 6 oxide? It's going to be lowered. And that is that on pressure. Now moving on to temperature. Now, temperature favors the reaction that is endothermic. Let me just briefly discuss endothermic and exothermic reactions. Now, when we talk about an endothermic reaction, this is a reaction that absorbs heat energy from the surrounding. Exothermic reaction gives off heat energy. So you have the system giving off heat energy to the surrounding. Now again, remember Le Chatelier's principle? If you change any of the condition, the system will work in a way that opposes that change. Now, if we are to increase the temperature, what will the system seek to do? Lower it. If you lower the temperature, what will the system do? Increase the temperature. Now again, let's do the two examples for the Haber process and for the contact process. Now for the Haber process, we can clearly see that at the end of this equation, we have an enthalpy change that is given. Now this has a negative sign. Negative sign simply implies that this reaction is exothermic. So that means that the forward reaction for the production of ammonia gas is exothermic. So when you react nitrogen with hydrogen to form ammonia gas, this reaction evolves heat energy. Now, what will happen if we increase the temperature? If you increase the temperature, the system will seek to reduce it. How does it reduce it? By favoring the reaction that will absorb any of the excess heat energy. And this, of course, is the endothermic reaction. So it will favor the backward reaction. So you're going to have ammonia breaking down to form nitrogen and hydrogen gas. Now, just to make something clear, if you have a reaction and you're told that the forward reaction is exothermic, then the backward reaction will definitely be endothermic. Now, if it's the reverse, if the forward is endo, the backward is exo. As such, they work as such. Now, our forward reaction here is exothermic. That means that our backward reaction is endothermic. So if you increase the temperature, it's going to favor the endothermic reaction because the endothermic reaction will absorb heat energy, therefore lowering the temperature. Now, what about if you decrease the temperature? If you decrease the temperature, what will happen is that again, it's going to favor the reaction that will increase the temperature. You're decreasing the pressure, I will increase it for you. So which reaction is that? Exothermic reaction. So the exothermic reaction is going to be favored because it gives off heat energy. And this, of course, will cause the system to have an increase in heat energy. So I repeat, you decrease the temperature, the system will forward the reaction that will increase the temperature, and that is the exothermic reaction. So you're going to have the forward reaction taking place, which will result in a higher yield of ammonia being formed. Now, on the Haber process, we are saying that lower temperatures are actually better for this, but you cannot have temperatures that are too low. This is because they will actually end up slowing down the reaction. Remember, temperature provides kinetic energy to particles. So if you have low temperatures, particles are going to have low energy, so you're going to have a slower rate of reaction. So low temperatures are not economical because the rate of that reaction will be slow. So what happens is that an optimum temperature of around 400 over around 500 degrees Celsius is used. Now moving on to the contact process. Now the contact process also has a forward reaction that is exothermic, as you can clearly see from the enthalpy change. So that means that an increase in temperature will not forward the forward reaction because the forward reaction is exothermic. Instead, it will favor the backward reaction, which is endothermic. So you're going to have a lower yield of sulfur 6 oxide. What happens if you decrease the temperature? It's going to favor the exothermic reaction because the exothermic reaction will give off heat energy, therefore increasing the temperature. You lowered the temperature, it increased the temperature by favoring the exothermic reaction. So more yield for sulfur 6 oxide. But just coming back to it, the best temperatures are supposed to be lower because they will favor the forward reaction. But again, just like with the Haber process, you cannot have temperatures that are too low. It will just end up slowing down the reaction. So the optimum temperatures that are used for the contact process are 450 degrees Celsius. Now for the last one, a catalyst. A catalyst only speeds up the rate of a reaction. It does not affect the position of the equilibrium. That simply means that a catalyst does not care whether it's actually the forward reaction or the backward reaction happening. It simply ensures that equilibrium is attained, and that's it. So it does not have any effect on the position of the equilibrium. And that is that for now. I'll be posting a video discussing past KCSE questions on the factors affecting equilibrium. Please watch it to test your understanding of this. See you there.